Alright, welcome back guys. We're going to look at some preparatory material for 8.4. I think some of this stuff you'll probably already know how to do. Just wanted to kind of review on some of it. Because in 8.4 we're going to be multiplying binomials and some trinomials a lot, so just get a little bit of extra practice right here. Okay, so, to multiply these, we're really just using the distributive property. Okay, we're going to take both of these terms in this first set of parentheses and multiply those to every single term in the second set of parentheses. So remember, we can always draw our little arrows. So we'll say x times x squared is going to give us x cubed, because we add those exponents. And then x times negative xy, well, the positive times the negative will give us a negative. The x times x will give us x squared, and the y is going to stay the same. And then x times y squared is just going to be xy squared. And then we're going to distribute the y on the bottom. So y times x squared is going to be, it doesn't matter the order. I'm going to put the x squared first and the y second, because that'll remind me that here in a second this term can get combined with this term. And then we've got y times negative xy. So again, a positive times a negative is a negative. The y times y will be y squared, and the x will just stay the same. And then finally, the y times y squared is going to give us y cubed. Okay, so that's the multiplication. Now what we need to do is combine any like terms that we have. So that's one of the reasons I was concerned about the order. Technically the order doesn't matter, but it's easier to find them if they're already in the same order. So you can see here I've got this negative x squared y that I can combine with this positive x squared y. And when those actually combine, they're going to cancel, guys, or in other words, become 0. And then furthermore, this term xy squared with negative xy squared, the same thing's going to occur. And so we get lucky because most of those terms cancel out, so we're just going to be left with x cubed plus y cubed. Okay, so let's try example 2. Now example 2, we've got this binomial that's in parentheses, and there's an exponent of 3 here on the outside. So this 3, this is an exponent again, so this means we're going to be multiplying this binomial by itself 3 times. So you've actually literally got to write it out 3 times. T minus 4 times t minus 4, and then times another t minus 4. Okay? And then the rest of this, guys, is just multiplication. So just start off with your first 2 binomials. So t times t is going to be t squared. T times negative 4 will be negative 4t. And then here on the bottom, negative 4 times t is another negative 4t. And negative 4 times negative 4 is a positive 16. And if we combine those two in the middle, negative 4 minus 4 is negative 8. So we're going to end up getting a trinomial. And I'm going to put it back in parentheses because now we have got to multiply it to that last binomial. Okay? So now this looks like the last one that we just did. So, well, I sort of ran out of room here. Actually, let's just pick this up over here where we got more room. I'll rewrite it. Okay, and so just start taking, each of these terms in the first set of parentheses and multiply them to those two terms in the second set. So we're going to have t squared times t which is going to be t cubed, and then t squared times negative 4 will be negative 4t squared, and then let's distribute the negative 8t. Negative 8t times t is negative 8t squared, and negative 8t times negative 4 is going to be positive 32t. And then finally we'll distribute the 16. 16 times t is 16t, and 16 times negative 4 is negative 64. Okay, and then we got to combine our like terms. So we got a couple of them here in the middle. Negative 4 and negative 8 will be negative 12t squared. Bring down your t cubed, and then we got another couple. 32 plus 16 is 48t, and finally we got the minus 64. Okay, so this is going to be our product. All right. Okay, now what we're going to look at are complex numbers, or I guess more specifically, numbers that have this imaginary root. Now we've talked about this sum in this class. We know, whenever we have a negative number under the square root, we're going to get an I. Okay, and the reason this occurs is because when you factor it, negative 9 is the same as 9 times negative 1. And we can take the square root of 9, it's just 3. And then by definition, this definition right here, guys, this tells us what the imaginary root is. It is defined to be the square root of negative 1. So that's where the I comes from. So the square root of negative 9 is what we call a purely imaginary number, 3i. And the reason we're going over this is because here in Chapter 8, when we're finding zeros of these polynomials, some of those zeros are not going to be real numbers. They're actually going to be complex numbers or purely imaginary numbers. But they are zeros nonetheless. All right. Oh, there's one other part of this definition that I want to mention right here. The fact that I squared is equal to negative 1. I want to show you why. So we know that I is equal to the square root of negative 1. So if we square that, I squared would literally be square root of negative 1 times the square root of negative 1. And if you multiply these, the square root of negative 1, negative 1 times negative 1 is 1. And the square root of 1 is 1. Okay, so that's where we get that second definition. And we will need to know this here in just a minute. We got to remember that if we square I, we get positive 1. Okay, so let me talk about the complex numbers for just a little bit. The complex numbers, okay, so far in this class we've really only focused mainly on real numbers. So real numbers are basically any number you've come into contact with for the most part, other than I. Okay, but complex numbers are actually a larger set of numbers. It's a bigger set that includes the real numbers, and it also includes the imaginary numbers. And so for that reason, complex numbers can be written in this form. Okay, a plus bi. And what this means is that a represents the real part of your complex number, and then the bi represents the imaginary part of your complex number. Okay, so you could see that if we did away with the real part, we would end up with just the imaginary numbers. And if we did away with the imaginary part, we would end up with just the real numbers. But complex numbers are made up of either just a real or an imaginary, or made up of a combination of both. So it's this larger encompassing set. Okay, and you can see that illustrated down here in this diagram. So the set of complex numbers is the largest set, and then within that we've got these what we call subsets or smaller sets. So we've got the set of all real numbers, which can be broken down into the irrational numbers and the rational numbers. And then on the other side we've got the imaginary numbers, and these can be broken down to just the purely imaginary numbers or the imaginary numbers that have both a real component, the A part. Okay. Alright, and so what we're going to do now is look at actually how can we multiply complex numbers. Okay, we know how to multiply real numbers. For example, 4 times 6 is 24. But when we're dealing with complex numbers, or in other words, numbers that have the imaginary root in them, how can we do this? Well, guys, it's very similar to multiplying algebraic expressions when you're using the distributive property. So if I had like 4 times x plus 7, you know, to multiply these, we have to distribute, in other words, and we get 4x plus 28. Well, that's kind of how we're going to treat or approach multiplying these complex numbers. In fact, that's how we're going to start this first one. What we technically have here, this negative 4i is a purely imaginary number times this other complex number that has both a real and an imaginary part. Okay, but the way we're actually going to multiply this is by distributing. Okay, so we're going to say negative 4i times negative 7. We know negative 4 times negative 7 is 28, and you're just going to keep the I. So when you're multiplying these i's, it's similar to x's. And then negative 4i times this 2i, that's going to give us a negative 8i squared. You can't forget the squared part, okay? Just for the same reason that x times x is x squared, I times I is I squared. And now once you've done your multiplication, you're going to see if you can simplify any of this. Well, this is why I emphasized that second part of the definition of the imaginary root, the fact that I squared is equal to, oh, wait a minute. No, this is actually wrong, guys. I squared is equal to negative 1. And the reason for this is because think about the square root of x squared. The square root of x squared is just x. And you can think about it like when you take the square root of something that's already squared, you just get that something, okay? And so, or another example would be square root of x and then that squared. Yeah, this is the example that's more pertinent. What happens is, you may remember from class, squaring a square root. When you square a square root, those are inverse operations, so they basically cancel each other out, and you end up with just whatever's underneath. So when you square the square root of x, you get just x. Okay, and that's actually what's going on right here. When we say I squared, we know that I is the square root of negative 1. And if we square that, we're squaring a square root. and so we get just the radicand or whatever's underneath it. So that's why this should be -1. Yes, I'm not sure what I was thinking there earlier. Okay, yeah, so this is what we got to know. All right, because anytime we see a I squared, like right here, we're going to replace that with -1. That's part of how we're going to simplify this. So we're going to be left with 28I minus 8, and then in parentheses, times -1. And so then you can actually multiply these. -8 times -1 is +8, and you'll still have the 28I, okay? And at this point, guys, you're basically finished. You cannot combine these two. Just like you can't combine these two terms over here because they're unlike. These aren't really terms, but they're different types of numbers. This is a real number, and this is an imaginary number. So because of that, we can't combine them. However, we do want our answer to be in this form, this a plus bi, in which the real number comes first, and the imaginary number comes second. And so because of that, I'm going to swap the order here. I'll put my 8 first and then my 28I second. Okay. And the homework may even tell you to make sure you put your answers in this form. Okay, so 8 plus 28I. So this is our result, and this is another complex number. Okay. All right, let's do a couple more. Okay, so here you can see we are multiplying two complex numbers. Each of these has a real and an imaginary component. And guys, just like multiplying two binomials, we're going to multiply these by distribution, or you could remember the FOIL acronym. But we're going to say 5 times 7 is 35. 5 times -8I will be -40I. 3I times 7 will be 21I. And then 3I times -8I will be a -24I squared. Okay? So you've got to remember that when you multiply those two i's, you're going to get I squared, because we're going to replace this with -1 here in a minute. All right, now what you could do, these two numbers in the middle, these are both imaginary numbers. These are sort of like terms. They both have just an I, so they're two imaginary numbers, so we can actually combine them. -40I plus 21I will be no, that's not right. It will be -19I. And then drop down on -24, and I'm going to go ahead and replace the I squared with -1. And so the -24 times -1 will become +24. And then we can combine the two real numbers here, guys. The 35 and the 24, that's going to give us 59. And then write your imaginary number, the -19I, second. Okay, so now we have it in that a plus bi form. And so this is another complex number. You may be wondering, well, what are these complex numbers used for? They're used for, you would see them a lot in physics, guys. For example, in circuits, designing circuits and things of that nature. Electromagnetism, I know, is another field in which they're used a lot. Basically, things that have two components, or that sort of come in pairs. These imaginary numbers are useful to model that type of behavior, because these imaginary numbers, it's sort of like a pair of numbers. It's a real and an imaginary number. All right, let's do one more here. We're going to do it the same way. Now, I do want to point out, though, these are what we call conjugates. They're basically the same, but they have different signs. These are called complex conjugates, and whenever you multiply two conjugates, something special happens, and you'll see. So 4 times 4 is 16. 4 times negative 5i will be negative 20i. 5i times 4 will be positive 20i. And then 5i times negative 5i will be negative 25i squared. And what I was alluding to will happen is that these two imaginary terms, or numbers in the middle, guys, will cancel. Technically they give us 0i, but 0 times anything is 0. So we don't need to even worry about that. And so we'll be left with 16 minus 25, and I'm going to replace the I squared with negative 1 again. And so negative 25 times negative 1 is positive 25. And if we add that to 16, we are going to get 41, which is a purely real number. So this is what's interesting about this. When you multiply two complex numbers and they happen to be conjugates of each other, you get actually a purely real number as your result. Okay. And just real quick, I do want to show you, you can do these in your calculator. I'll do this last one. So you got to type them in the same though. 4 plus 5. Now the I is down here, okay, right above the period. It's in blue, or the decimal rather. And then you can close those parentheses and then do the same thing. 4 minus 5i. And the calculator can do complex arithmetic. So anyway, alright, well I hope you find this helpful, guys, and I'll see you in class.